Okay, quick review from yesterday then. What did we talk about yesterday actually? We talked about fields. Had a brain fart for a moment there. What's the point of a field? Sure. Okay, in electrostatics it'd be about how charges would react. Is the only type of field though electric field? Sure, and we'll actually talk about magnetic fields later as well. The idea would be to describe what would happen at a distance away from an object. I use the term action at a distance. You can be bolding that word there. Like, I mean, you can have forces where I'm pushing stuff, right? Where I'm physically touching. But we want to discuss forces now where like, obviously things are going to be moving, but, I mean, it almost seems like magic, right? Like, why does, a magnet cause this thing to happen way over there? Why does gravity cause this to fall when they're not actually touching each other? Does that make sense? So a field is used to describe a three-dimensional region of influence, basically describing a strength at a certain distance away. I like using gravity as a good place to start. Gravitational field strength on Earth is 9.81. But as you go further up in altitude, that field strength would not be 9.81, it would be 9.80, 9.79. Does that make sense? The further away from Earth you get, the weaker the field is. Does that make sense? Okay. When we talk about electric fields then, we're always talking about how a proton or how a positive charge would react. Okay. So in terms of like drawing field lines, we always draw field lines from positive to negative. Does that make sense? This is going to be kind of confusing in a bit because electrons, when we talk about electricity, electrons flow from negative to positive. I'm going to say that one more time. Field strength, we've defined a field as being what a positive charge would do. So a positive would go from positives to negatives. Does that make sense? This is going to get confusing though because if we ever talk about electricity, electrons want to flow from negative to positive. So you gotta make sure you keep that straight in a little while when we talk about the difference between the two. Does that work? Okay. Let's talk about something called electric potential then. A very common scenario is that you're gonna have two plates. And we're gonna make one of the plates become negatively charged and one of the plates become positively charged. So rather than having just like a single point charge, we'll have like an entire plate. Okay. What's gonna happen here is you're gonna have field lines then between these two plates. And I stole this diagram from yesterday's notes. Which way would the arrows be pointing then?
Towards the negative.
Because a field describes what would happen to a positive test charge, right? And a positive test charge would be repelled from the positives and attracted to the negatives. Does that make sense? Okay. Imagine that you had just a proton just sitting here. What forces are acting on the proton at this particular moment?
Pushing away from positive.
Okay, so I'm going to go up, and I'm going to say that there is an electrostatic force pushing this thing upwards. Well, it's the same thing though, right? Like the positive is being attracted to the negative or pushed away from the positive. Either way, it's kind of the same concept, right? There's actually one more force that would act on us, though. Okay, gravity. Yeah. There's a really famous experiment called the Millikan oil drop experiment. I'm actually going to have you guys research this as part of your lab. But the basic idea behind this experiment is a guy set up two different plates. Okay? And then he adjusted the amount of electric field strength such that the electric field strength pulling this thing upwards matched the amount of gravity pulling it back down. And these particles, they just hovered there, right in the middle. Does that make sense? Okay. One of the terms I need you guys to know is called voltage. And I'm going to guess that you've heard that term at some point in your life. Like how much volts something has, or like a 9-volt battery, 12-volt battery. You guys heard that phrase before? So there are a lot of different like synonyms, I think that's the right word, for voltage. So it might be called voltage. It might be called potential difference, might be called electric potential. So anyways, all of these terms in terms of physics though, they mean the exact same thing. Okay. I'm just going to read my paragraph at the top here. Electric potential energy is going to be similar to gravitational potential energy. At the top of this diagram right here, a positive test charge would have a lot of potential energy. Say you have a proton sitting right up here by this positive plate. Positive and positive will want to repel each other, right? And so this proton, ignore gravity by the way just for a second, because that kind of screws things up. So imagine maybe that this is like flat surface rather than like vertical. Okay. Thanks. This proton right here then would want to move this way. Why? Well, the positives will push it away. Also, the negatives will attract it. Does that make sense? So up here, there is a lot of potential energy. And then as this thing comes down here, there will be low potential energy. Where's the energy change to, though? Nope. Where the energy change to? You can't just lose energy. So if you used to have a lot of potential energy up here, there you go. Good job. Right down here, you're now going to have high kinetic energy. What's kinetic energy's formula? I don't imagine the mass of your proton will
Please excuse
change.
interruption. Mr. Laverato,
Right.
please call 100.
What will it change?
Mr. Laverato, please call 100.
Your velocity. Right? Up here, imagine that you just stick a proton right there. What's going to happen is the proton will then move towards the other plate. It will go from a velocity of 0, because you're just going to stick it there, right? You'll start with nothing, to a velocity of, I don't know, something. Does that make sense? So we can actually consider this sort of voltage and electric field thing very similar to energy. It's actually going to get really confusing in a slide. I mentioned this yesterday. If I do E with a little like bar thing over top of it, it means it's electric field strength. And if we do E by itself, it means energy. And we're actually going to work with both of those in different formulas today. It's going to be so frustrating. Just some more diagrams before we get to the math. So imagine you have a negative charge now. Which way is the field going? Got to really keep things straight. So here you have a negative charge, fair enough, but the field always is based on what a positive charge would do. So a positive charge would leave the positive plate and go towards the negative plate. Does that make sense? So even though the field is going upwards, the actual path of the electron, though, would be attracted to the positive plate. Does that make sense?
Wait, the positives can move?
Well, like, let's say it was just a proton, right? Like, if you just had a positive would go this way. So, by definition, we always draw a field as what a positive charge would do. Okay? So the field is going to go upwards. But we're not talking about a positive, we're talking about an electron, which is a negative. So then it'll go the opposite direction. It'll repel from the negative plate and attract to the positive plate. You're really going to need to make sure you keep those sorts of things straight, because fields are like how protons would react, but we'll often work with electrons, which are going to be the opposite. Just kind of what I was trying to say with electricity earlier. Electricity, electrons are going to run from negative to positive, but that's not how a field is defined. Can you keep that straight in your head? Okay, here's the math. Alessandro Volta is the guy basically who we named the Volt after. Maybe you've heard his name before. They've also named, is it the Chevy Volt? Is it Chevy that does the Volt? An electric car? Anyways. A volt is actually known as a joules per coulomb. But rather than call it a J over C, we call it a capital V instead. Here's the formula for it. If you want to find a voltage, you have to know how much energy it takes to move a charge. That makes sense? If you want to figure out how much voltage there is, we have to figure out how much energy it will take to move a charge. Here is energy, and Q is charge. That makes sense? I have another term up here. You could also look at it as like the work done on a charge. But you're going to want to divide by how much that charge is. For example, let's say you only have to move 1 coulomb. Well, that would be different than if you had to move like 12 coulombs. Does that make sense? So the energy is part of it, how much work you have to do. But the other part of it is like, well, how much charge does the actual object have in terms of like positives or negatives? Another thought here, this is actually a scalar quantity, so we don't need a direction for voltage anymore, which is kind of nice. Also good because these guys don't have like the little, I don't know what to call those things. Sure, ticky things. The things that imply vectors, which is really important because this E right here is not field strength, it's energy. So frustrating. Okay. Before I do some more math, I just want to talk a bit about some relations to like other things you guys are familiar with. Most importantly, a battery, because I imagine most of you guys have heard of volts with batteries before, right? So, the way a battery works is batteries often have two different plates in them as well, actually. Anodes and cathodes, if you've heard that term. And for you guys in my Chem 30 class, this is our next unit, by the way. We're going to talk about how batteries work. The idea is basically going to be, though, that your electrons are going to leave the negative plate and are going to be attracted to the positive plate. Does that make sense? And as the electrons run through the circuit, if you attach like a light bulb or something in between here, then the light bulb can shine because it'll cause electricity to run. Does that make sense? Okay. In terms of the battery here? There's actually, this is a tougher question to answer simply. It's going to be chemicals that are going to be in between here. And what's going to happen is these two chemicals are actually kind of in contact with each other. Like usually there's some sort of barrier in between them. And what happens is this stuff over here, it's going to try to lose electrons. So that they go this way right here. And then they'll go all the way through the circuit here.
Is that why batteries die?
Yes, because eventually the chemicals will have had all of their electrons transferred from like one side to the other. We're going to do this in chemistry, if you don't mind holding off on that thought a little bit. That's okay. It's kind of tough for me to answer it without going into like a whole electrochem spiel.
Sorry.
That's okay. What's up?
Aren't like car batteries usually made out of lead and acid?
Yep. Yeah, I can actually show you some of the chemical reactions if you guys would like for how that works in terms of redox chem. Well, okay, why don't I see if I can find it right now since you're asking. This may not make complete sense because I'm kind of giving you a partial picture of chemistry, but if you guys are in my chem class and you have your data booklets, see if you can find your data booklets. Do you have them with you?
Yep.
There's a table that we'll use in chemistry at some point. See if you can find this table here. I'll see if I can do my best to explain this in like a succinct manner. Okay. In terms of relation to chemistry, right over here is a table, or is a, oh, what did I do? Right over here is an amount that's going to measure how many volts something has from a chemistry perspective. You guys can see this over here. Sometimes in chemistry we'll call this E with the little symbol there. We call it electric potential, but it's the same thing. Okay. The way that these chemistry reactions work is you always have to have two reactions happening simultaneously, one for each of the positive and negative plates in a battery. Does that make sense? This one right here is the one that Sean, you mentioned. This is what a car battery runs on. And so it basically goes from lead 4 oxide and some sulfates and hydrogens. Okay. What's going to happen here, though, is this guy right here needs to gain some electrons. You see how like electrons are part of the reaction? And so usually you have to have another reaction go with it. I don't actually know off the top of my head what the other car battery reaction is, but it might be, where is the other lead one on here? Lead. It might be this one right here. And so what usually you have to have is one reaction happens at one of the two poles. We call them either anodes or cathodes of batteries. You guys heard those terms before? Like the positive and negative pole of a battery. And then you'd have another reaction down here. And it's all about, see how like electrons are sitting in here? That's kind of like the quick version of it. Does that help answer your question? I can talk to you guys more later if you want. Sorry, that's not a full picture. Okay, another term I want to talk about, just so you don't get them confused though, is the term current. Okay. Current is about how fast electrons move. It's like a speed. Current is a measure of coulombs per second. I like to think of this similar to like a velocity. The faster the electrons move through your circuit is current, but that's not voltage. Voltage is the energy difference they have per charge. Say that one more time. If you ever hear the term current, current is how fast things are moving through a wire. So like the electrons are zipping really fast, there's a lot of high current. Voltage is how much energy they gain per the amount of charge you have. So they're different things. I've got another analogy that maybe will help make sense. Imagine that you've got water flowing from like a water tank. What would cause the water to fall out of the tank? What force is going to cause it? Gravity. Yeah, gravity. Okay. So up here, there is a lot of potential energy. Does that make sense? And when you get down to the bottom here, you're going to have a lot of kinetic energy. A battery works kind of in the same way. Okay? Your electrons are going to want to flow away from the negative pole towards the positive pole of the battery. Does that make sense? But it's about how much energy they have. Right here, the electrons have a lot of potential energy to move. And then they run through your wire, they turn on a light bulb, they show up over here. I mean, you used to have a lot of electrons here to start, and then those electrons will move through the pole, and eventually all these electrons will be here. And then once all the electrons are there, your battery's dead. Unless you have a rechargeable battery, in which case you actually force the electrons to go back the other way, so then they can come back again, and the electrons basically do circuits all the time. That makes sense. So let's look at what your iPhone does. When you plug it in at night, the charger in the wall is causing all of the electrons at the positive pole to go back up to the negative pole, and then when you take your cell phone out of the charger and it starts working again, then the electrons go back the other way. Does that make sense? Okay. So, anyways, the point I want to make here is about energy, though. Okay, voltage is about the change in energy from here to here. If you ever hear the term current, current is about how fast it happens. That makes sense. So, in terms of like water flowing through this pipe, what would make more water? Like, what would make water flow through this pipe faster? A bigger pipe. Yeah. If you had like a little hole, sure, water will flow out, but maybe it's just leaking, like it's dropping drip by drip by drip. Is the energy difference still the same? Sure. You still have energy from high to low down here in terms of potential energy. That's if like it's dripping. If you were to like put like a massive hole in the side of this water tank and it comes rip-roaring out of there, well, now the water's coming through faster. In terms of electricity, that's current. So, I found this slide on the internet here that kind of describes some of the similarities between water flowing and electricity flowing. But I think I'll just leave that for you guys to read if you want. That's not really the key to the section. So let's work with that formula I just showed you then. Because to be honest, the math is not necessarily hard. It's just knowing which formula to use. Okay. If you want to find a voltage, voltage is a change in energy divided by how much charge there is. So this one's pretty straightforward. I'm going to give you the amount of energy change this thing's going to get. So 2.6 times 10 to the 3 joules. I'm going to tell you how many coulombs this guy has for charge, so just divide them. Yeah, it's going to need to be in joules, and then when you're done and you get a joule over a coulomb, call it a volt instead. I got 765, although I only get 2 sig digs. 764.705?
Yeah.
Okay. So with sig digs, I've got 7.6 times 10 to the 2, and we'll call that a volt. So that's the energy change for an object between two plates. So maybe if I can visualize this, imagine that you've got a negative plate up here, you've got a positive plate up here. Okay. If you like the battery example, electrons will actually run through a wire like this. Okay. But this probably isn't a battery currently because this guy right here is a positive charge, so kind of ignore that thought. Give me 1 second if you could. So a 3.4 coulomb charged object, imagine that this right here is 3.4 coulombs sitting on this plate right here. Okay. What's going to happen to this positively charged object? Will it just sit there? No. If this guy's positive and this guy's a positive plate, which way will it move? Sure, up, yeah. And so it's going to then have an energy change. Does that make sense? And so the voltage is defined as how much energy change there would be divided by the actual charge on the object. The more the charge on the object, probably the faster it's going to move from one plate to the other, right? Does that make sense? Do you still have your question?
We could find the distance it went from the information found.
From one plate to the other?
Yeah.
That's actually coming up. Yeah, you're right. Another term I need you guys to know is something called an electron volt. Okay. Often when we're working with this, the amount of energy is fairly low. Okay. And so what we do is we've defined, and this is going to be confusing again, a volt is actually a measure of voltage. An electron volt is a measure of energy. Okay. A volt equals a volt. Okay. But an electron volt is actually a fancy way of measuring energy. Energy. Okay. And here's the way this works here. An electron volt is the amount of energy that it takes to move one electron, 1 volt. So there's a number I need you guys to know, but it's on your data sheet. Okay, here's the proof for it. If V equals E over Q, does it make sense that I can bring Q up over to the other side? That makes sense. Okay. Well, if Q is going to be 1 electron and V is going to be 1 volt, do you guys remember how an electron is equal to this many coulombs? You guys remember that relationship about electrons to coulombs? So the long story short is that if you have an electron volt, it is that many joules. So when we have like just a little bit of energy, rather than writing it with like times 10 to the minus 19, we might call it an electron volt. Is this on your data sheet somewhere? I'm fairly certain it is. Yeah, it's right under Coulomb's law constant. So if I ask you to solve for an electron volt, you're actually solving for energy and then convert it when you're done. So let me show you an example. We're going to try to figure out how many electron volts are needed to move an alpha particle based on this voltage. So first thing, if you're looking for electron volts, you're actually looking for energy. I know it's confusing. So V equals changing E over Q. We have the voltage because we were given that. You might be given information on subatomic particles, like what's called an alpha particle. I pulled this out of your data booklet. An alpha particle has a charge of positive 2e. What is E? Okay, and so like in terms of E, if you go back up there, E is an elementary charge, which is 1.6 times 10 to the minus 19. Can you guys see this in your data sheet? It's E equals 1.60 times 10 to the minus 19 coulombs. So this E right here is actually not an electron. If you read it like this, E with a negative, that's an electron. This E right here refers to an elementary charge, which is this many coulombs. It could be an electron, but this is actually positive. So we need 2 of those. So this is 2 times 1.60 times 10 to the minus 19 coulombs.
Is this little E on our calculators that number?
No,
Oh, why
Sorry.
not?
that's a completely different thing. All right, so let's times these together to get the change in energy. So E could stand for electron, but it actually stands for an elementary charge, which could be negative or it could be positive. This one, by the way, is positive, so that's why I don't want to call it an electron. 7.6 times 10 to the power of 2 times 2 times 1.6 times 10 to the minus 19. I got 2.432 times 10 to the minus 16. Okay. What would the units for this be? It would be joules, yes. So here's why we have the concept of the electron volt. It's kind of silly to have numbers be so ridiculously small for joules. Like this is very, very little energy. So what we'd like to do now is convert this into an electron volt. So take 2.432 times 10 to the minus 16 joules and multiply by that electron volt number, which is 1 electron volt for every 1.6 times 10 to the minus 19 joules. Does that make sense? So I know you just times by 1.6 times 10 to the minus 19. We're kind of now redividing by it again. So I got 1520 electron volts, and that would be your energy. Does that make sense?
Wait, what?
Lost you there? So we got energy right here in joules, but it's such a small, insignificant amount of energy, right? It's hardly noticeable. So another unit of measuring energy is called an electron volt, which is a really small amount of energy. Okay. And so the ratio for that is 1 electron volt is the elementary charge number of joules. So basically take the number you have and divide by 1.6 times 10 to the minus 19. Hopefully you get 1520. Do you guys get 1520?
I didn't put in times 10 to
Oh, okay. Last thing is I better do sig digs, so 2 it looks like. So 1.5 times 10 to the 3 electron volts. Big note here though, this is energy. I wish I could rewrite physics history and make things a little less confusing because a volt is a voltage, but an electron volt is energy. E is energy. E with a line over top of it is field strength. Like someone should have done a better job of organizing this. Okay. You can play around with formulas a little bit. Sean, you mentioned the concept of solving for a distance. We can actually do that. You guys remember how work is equal to force times distance? Formula there? Well, if work is equal to energy, probably pick it up right about here. Voltage is equal to E over Q. But if energy is equal to work, and work is equal to force times distance, you see how I'm kind of like putting formulas inside of formulas? And then what we can do here is we can kind of separate this a little bit and say rather than force times distance over Q, let's just go with just force over Q with just distance sitting off to the side. The reason why that's relevant is that force over Q from yesterday is actually equal to electric field strength. So we actually have a new formula here where a voltage is actually equal to an electric field strength times a distance. So we can actually solve for the distance between the two different plates in a battery or whatever the field is that's causing the field between them. So usually we write it like this though. This is the way it's written. Electric field strength is equal to a voltage over a distance. In terms of units, there's two main ways of describing a field strength then. You could go with newtons over coulomb, or you could go with volts over meters. Okay. I need to point one thing out before we do some more examples here. This formula only applies to plates. This formula down here applies to like point charges. Does that make sense? Just like a single charge, yeah, like a single item. Okay. So there are two different formulas on your data sheet for electric field strength. I think there's actually more than two. Because you've got E equals Q over R squared. You've got E equals FE over Q. And you've also got E equals V over D. So just keep in mind that that last one there is only for plates, and the two above it are for charges. And then the one where it's V equals E over Q, that's actually not field strength anymore, that's now energy. Keep it straight. Good luck. So let's do some more examples. So we've got two parallel plates. I'm going to tell you the field that we want between them. Let's figure out the voltage. So, because it's plates, we can use the formula E equals V over D, but I gotta be careful here. This needs to be the E with the ticky thing on top. So this will be 800 newtons per coulomb. Do you guys remember the other way we can represent field though, rather than newtons per coulomb? On the last slide? Volts over meters, yeah. So even though they wrote it as newtons over coulomb, you may want to write it as volts over meters just to make more sense. You're going to want to times that distance up there. So the distance is currently in millimeters. So I've got to change that, right? So if I multiply by 0.0160 meters, that should get me a voltage. So I got 12.8 volts. For the first little while, you may need to remind yourself every time you do voltage. I do, because I'm not nearly as familiar with this as I'd like to be, what a voltage is. A voltage is how much energy it takes to move a charge. That makes sense? To make a charge move from here to here, how much energy is it going to take to move that charge? That makes sense? Let's figure out the work done if an alpha particle moves from the positive plate to the negative plate. How do I solve for work?
Energy.
Okay, so we could do force times distance. I have a distance. Do I have a force right now? Okay, Sean, you just mentioned something. Energy is work. So we have a formula for a voltage is equal to energy divided by charge. Energy is work though, right? So how do I get energy by itself? Take your voltage and times by a charge. Well, we have a voltage, 12.8 volts. We just solved for that. We just need to know the charge on an alpha particle. We did this a few slides ago, though. What's the charge of an alpha particle? 2 of them, though. Times 2. Yeah, an alpha particle was, Forster, 2 of an elementary charge.
Do you need any more of these?
No. So a voltage times 2 times 1.60 times 10 to the minus 19 coulombs? Yeah. Do you guys remember what a volt was equal to in terms of other units from the previous slide? Volts are a joule per a coulomb. So rather than write it as a volt, it may be worthwhile for me to write it as a joule per coulomb so that the coulombs can cancel. So 12.8 times 2 times 1.6 times 10 to the minus 19. So I've got 4.096 times 10 to the minus 18 joules. That makes sense? So with sig digs it should be 4.10. That make sense? Okay. Well, this is energy, right? Work is energy. So, I mean, if you need to visualize this, draw like a positive plate, draw a negative plate. These plates are 16 millimeters apart. An alpha particle, let's say the alpha particle started at the positive plate. Okay, this guy's a positive charge. What's going to happen to this particle? He's going to leave the positive plate and go towards the negative plate, right? So is this an increase in kinetic or potential energy? Kinetic.
Oh,
Because what's happening is if it's starting at the positive plate, right, is this guy going to want to stay at a positive plate if you're a positive charge? No, right? Positives will repel each other. So up here he has potential energy, and then over here it's going to have kinetic energy. I mean, I imagine eventually this particle is going to bash into the other plate. Does that make sense?
How do we know that the positives are on the top though?
I just drew them that way. It wouldn't make a difference though. I mean, you could have it as side by side like this and go positive here, negative here. Here's a positive particle on the positive plate, because it told me that, right? Will a positive particle want to stay by a positive plate? No. It's going to want to move that way. Which, by the way, is the way the field would be drawn, because the field gets drawn from positive to negative. It's just confusing if you're doing electrons instead. So
If it was twisted, so the positives were on like the bottom, and then the negatives were on the top,
okay,
would that mean that they would have an increase in?
well, we're talking potential energy, but like electric potential energy. Ignore gravity here. I think because I'm guessing what you're thinking is that gravity is going to cause this thing to fall down here, but we'll try to not consider what gravity would do at this particular moment.
Okay.
Right? Just deal with what the electric forces would be like. So I mean, if I were to draw that and you were to have positives down here, negative plate up here, and you put the positive particle here, right? This positive particle would want to go that direction. So here it would have potential, and here it would have kinetic.
Oh, okay.
Does that work?
Mhm.
So I know that down is this way and gravity acts down, but ignore gravity for right now. We're not considering gravity.
Okay.
That makes sense? It's kind of frustrating. At least it is for me. I don't know what it's like for you guys. But here I have E equals V over D. But then I have to use a completely different E and consider it as energy. But the link between it is that this voltage right here was this voltage right here. So in theory, you could have E be electric field strength in a formula, as well as E be energy in a formula. Okay, let's try another example. Still alpha particle. It's going to be that far apart. There's the voltage. Let's find some force.
Don't use the B equals E over Q and then change it to,
Say that one more time.
you have to use the B equals E over Q, right? And then,
Oh, that one there, yeah. Changing E over Q. Okay. But this energy right here is force times distance, right? So voltage is really force times distance over Q. So we have the distance. We have the charge, because it's still an alpha particle. And we have the voltage. Divide out Q and, or times out Q and divide out D. That makes sense. So this is 130 volts. Only rather than calling it a volt, I think I'd rather call it a, what are the other options? Joules over Coulomb? Rather than call it a joule over a Coulomb, could I call it a Newton meter over a Coulomb though? Because a joule is a Newton times a meter. And then force is what we're looking for. Distance is what we have. And then again, it's still an alpha particle, so that is going to be 2 of your 1.6 times 10 to the minus 19 coulombs. So take this guy, multiply it up, take that guy, bring him down. Hello. Anybody want breakfast? I'll take a yogurt actually.
wait, how does that go down?
Well, I've got to take, because we want to get force by itself, right? So I need to get the 0.027 on the bottom and the 2 elementary particles up to the top. So let me show one more step here. You're going to take 130 Newton meters per coulomb. You're going to times by 2 times 1.6 times 10 to the minus 19 coulombs, so the coulomb cancels. And then you're going to divide by 0.027 meters, so the meters cancels. I got 1 point. How many sig digs do you get? 2? 2 sig digs. I got 1.5 times 10 to the minus 15 newtons. Did I? Okay. Any questions so far? How's it going? You able to wrap your mind around this? It's different, eh? Like all these units, at least for me, I can only speak for myself. I'm not as familiar with knowing how volts work and with how coulombs work, just because I don't do it on an everyday basis. In my mind, I can always kind of picture like what meters per second might look like, or what a newton might look like, just because I'm kind of used to that. But like, I have no frame of reference for volts or coulombs. You know what I mean? So it's kind of hard to like know whether this answer is reasonable. Like, is 1.5 times 10 to the minus 15 newtons a reasonable answer? Honestly, I have no clue. I'm just not familiar with that as much as I am with other things. You know what I mean? So. Okay, 2 last examples? 3 last examples. So, I'm just going to draw a diagram here. Now I'm going to work with an electron. And so again, remember, electrons are going to be a little different than protons in that electrons are going to go opposing the way that we have a field line if we're drawing fields. So I'm just going to draw 2 parallel plates. I'll draw it like this. Here's a positive plate. Here is a negative plate. And we're going to have an electron accelerated from rest between the 2 plates. I didn't say as much, but I'm going to assume that the electron is going to start at the negative plate, so that the electron then is repelled from the negative plate and goes towards the positive plate. Does that make sense? We get to know the distance. So the distance is 0.040 meters. And we also get to know the voltage, which was set to 20 volts. Okay. We want to try to figure out the velocity of the electron once it reaches the positive plate, using kinematics and dynamics. Give that hint there so you can remember how to do that. So. What do I have? What can I start with? What formulas are useful so far? I have a distance and a voltage, so that's field strength. So what we could do is say that your field strength is equal to your voltage over your distance. So my field strength is 20 volts over 0.040 meters. How does that help me? No, not yet. So I've got 500 volts per meter, if that's useful at all. Can I use that somewhere else, now that I have a field strength? Okay, so maybe that wasn't helpful. Yeah, we need to somehow get into some sort of force equation, don't we? Well, why don't we try that? So then your electric field strength is equal to... I'm actually blanking on how to solve this. I just looked it up before we started. All right, different idea here. Let's take our change in voltage and make it equal to our change in energy over Q. Maybe we can do that. We have a voltage, right? So we have 20 volts. Find our change in energy. We know Q, don't we? I know it doesn't come out and say it, but it was an electron. So what's the charge of an electron? 1.6 times 10 to the minus 19 joules. No, coulombs. There we go. Rather than write this as a volt, then maybe it's better to write it as a joule per coulomb. So if I times up the 1.6 times 10 to the minus 19 coulombs, I should be able to get amount of energy. So I've got an energy of 3.2 times 10 to the minus 18 joules. Yeah, that's actually what I wanted to do on the next slide. I'm stumped again on how I wanted to do kinematics and dynamics. That's way easier. Why don't we do the one on the next slide? Can you guys see how the one on the next slide is the exact same information, but it says using energy? Let's do that one instead. Because this one is the way I would solve it if I had to. I now have an energy. Your energy kinetic will be equal to 3.2 times 10 to the minus 18 joules. But that's equal to 1/2 of mv squared. It is actually, yeah. If you guys look in your data booklet, you can actually find the mass of an electron written in your data booklet. For some reason, I'm blanking on how to use kinematics now. 9.11 times 10 to the minus 31. So the mass is 9.11 times 10 to the minus 31 kilograms, v squared. So you have to times by 2, divide by the mass of the electron, and square root it all. Yeah. I got a velocity of 265.0518. That should be more than enough digits for right now. Anybody else get that?
Yeah.
265.0518. So in terms of sig digs then, I got 2 sig digs. So my velocity is 2.7 times 10 to the 6 meters per second. That's how fast that thing will be moving by the time it's gone through that field. Does that make sense? I'm running out of time right now. I'm totally blanked on how to use kinematics and dynamics. The reason why I did that though is I wanted to show you that energy is actually the easier way of solving things, because the way of doing kinematics and dynamics was quite frustrating. You have to use like find a force, find an acceleration. Once you have an acceleration, you have to use like a kinematics formula, and it takes like 8 times more work. So maybe I'll try to figure out how to do that again for